Welcome to another very interesting video on vectors with my student Akshit. We'll understand what is dot product and what are its applications. In case you want to learn from me, you can always send an email on the address given. Let us now understand the concepts and enjoy the journey of success. Hi Akshit, how are you doing?
Hi, sir. I'm doing great. How are you?
Very good, very good. So tell me, what are you doing at school now in mathematics?
Sir, in calculus, we're doing vectors right now, right? And we
Brilliant.
just finished our Unit 6 test, which is just on intro to vectors, right?
Okay,
And tomorrow our lesson is going to be on dot product.
perfect. So today you want to start with understanding what is dot product, right? That's
Right.
your idea. Okay, anyway, you had a test today. Could you share some question which was interesting? We can look into that type of question and then we'll move on to a new chapter, which is dot product for you. Okay? Tell
Yes,
me,
sir.
would you like to share some question?
Yes, sir. I had one interesting question in mind
Mhm.
where we were given a parallelogram in R cube, right?
Okay.
And we were given the three vertices and asked to find the other vertices, the missing one.
Okay. So let me sketch one and you tell me the
Yeah.
values. We'll try to figure this out. Right. So let us say we are given a parallelogram. Let me make one here. Let's say this is a parallelogram. Let us say, name what is this? Let's say A is what? Give me some random numbers.
Yes, sir. We can take A like 1, 2, 1.
Okay. B.
And B, we can say like 2, 3, 4.
Okay. D.
And D will say 5, 6, 7.
Perfect. That means you have this parallelogram in R3, right?
Right.
Tell me, how will you find the coordinates of C?
Right. So I labeled C to just be a general form of XYZ, right?
Okay.
And then I chose that vector CD, right? And I know that its magnitude would be, you would have to take away like 5 minus X and then 6 minus Y and 7 minus Z, right? For the magnitude.
Yeah.
And its magnitude would be equivalent to AB. So how I approached it is finding the magnitude of AB and then substituting it into the vector CD.
So when you use the word magnitude, in that case, it will be 2 minus 1 square plus
Right,
3
right,
minus 2 square plus 4 minus 1 square and square root, right? That is how you're going to
right.
get the magnitude, right? So when you say magnitude of AB, that will really be equal to, in this case, 2 minus 1 whole square plus 3 minus 2 whole square plus 4 minus 1 whole
Yeah,
square, correct?
correct.
That becomes the magnitude. And for the magnitude of D to C, it will be what? Let me write down. D to C will be square root of x minus 5
X minus 5.
whole square plus y minus 6
Yeah,
plus z minus 7.
right.
So how will that help you to find the value of xyz?
Right. So actually I substituted the magnitude of AB to be the same as DC.
So it is not the magnitude. It is the change in x value, change in y value, and change in z value. It's kind of like a gradient. You understand?
Oh, okay. Yeah.
So you are doing the right thing, but saying the wrong thing. That is
Yeah,
why
exactly.
you
Yeah,
get the idea. So you did a brilliant thing, and that is how you should be doing. So what you see here is that the the change in x value is what? So you can say delta x is actually 1, right?
1, right.
It increases by 1. So from 5, if I add 1, I get 6. Do you see?
Right. Yeah, that's what I did, sir. I think I'm
That's what it
mixing
is.
up my words.
And then from 2 to 3 is also plus 1. So this number should be 7.
7.
But from 1 to 4, it is plus 3. And so 7 plus 3 is 10. Do you see that? So
Yes,
we
sir.
get the coordinates of point C as 6, 7, and 10.
Right.
So you move the same. It's kind of a translation. So
Right.
you translate it from point A to B, and that is exactly equal to the translation from D to C.
D to C. Right.
And that is why we're just looking into the change in X value, change in Y value, and change
Yeah.
in Z value to get the new coordinate, right?
Yes, sir.
So that is how you get the coordinate points very easily without getting into details of distance formula. Is it okay?
Right. Yeah.
Good. So that is right. You got it right. Great. Let's now discuss about the new chapter which you have, which is called dot product. Correct?
Yeah. No problem.
Dot product. Now, dot product is a new name. We have never heard about it ever before, right?
Yeah.
First thing is, why is it there? We should understand. After all,
Right.
why do we have dot product? So, in general, you talk about multiplication, right?
Right.
Now, in vectors, we have kind of multiplication, but we have three types of multiplication, which we actually call multiplication is same as products, right?
Right.
So product of two numbers. One of them, which you learned earlier, was scalar product, right?
Right. Scalar part.
Or you can say scalar multiple or product, whatever.
Yeah.
Or scalar multiplication. So if I have a vector, let us say vector u, then 2u is scalar multiple. So the only thing
Right.
here is that the vector u, if it is represented by this arrow, then 2u will be twice the length in the same direction.
Yeah.
So that is scalar product. Now, we have a dot product now. So dot product is kind of very different. And let me first tell you, why do we have a dot product?
Yeah.
Mathematics is a language which tries to explain or model real life situations. That is the basic of mathematics, right? It helps you to do your daily work very efficiently, and it makes you understand how we can analyze the situation and go
Right.
about. Now, you have the, like in physics, you've done work done, right?
Right, sir. Yeah.
What is
done.
work done? Work done is force times
displacement.
right?
Yeah.
Displacement, right? Now, force times displacement, but again, work done, you also say, is a scalar quantity, right?
Right.
Force times displacement, and that is the work done, and work done is a scalar quantity. Now, we have to model this situation. How do we figure out what is the work done when a force of some unit, some newtons, is being applied for a displacement of a few meters? How do we mathematically analyze this situation? That is what dot product is all about. You get the idea?
Yes, sir. Sir,
So,
also,
yeah.
in this case, right, the work done would be scalar because you're multiplying two vectors, right?
No,
Force and displacement.
We never say multiplying two vectors. I know force is a vector, displacement is a vector, right?
Yeah.
So dot product is a scalar quantity.
Oh,
so
okay.
The multiplication term will not be used in vectors. Whenever we talk about vectors, we will use scalar multiplication. So better word is not product, scalar multiplication, dot product, and then soon you will learn cross product.
Cross product, yeah.
So cross product means you're multiplying two things, right? Those two are kind of factors, right? So cross product, which will be a vector quantity. And dot product results into scalar quantity. So in many applications, we found that, the result when we do physical quantities multiplication, for example, area's length into width, right? Right, volume. Now, these things are scalar quantities. They don't have any direction. Correct?
Correct.
They are scalar quantity. Torque is a vector quantity because when you have a torque, the object moves up or down.
Moves.
So
Right.
there is a direction involved in it. You get the idea. And
Yes, sir.
therefore, when this vectors, such an important topic, you can see the significance was
Yeah.
introduced. It was introduced to explain these physical quantities. You get the idea?
Right.
So
Yeah.
when we talk about two products here, we say dot product and we say cross product. Of course, we'll learn about cross product later, but
Yeah.
let us understand what their result is. Dot product results into a scalar quantity.
Yeah.
And cross product results into a vector quantity. Examples are in dot product, as I started with, work done. Area,
Yeah.
volume. All these formulae, you know, length into width, length with
Right.
height, multiplying in normal sense of physics, correct?
Yeah.
Results into mathematical modeling with dot product. And cross product will be like torque. Right. So when you, let's say this is an object, and if you kind of rotate, it may move up depending on.
Yeah.
So that is the direction involved in it. So that will be the cross product. You get the idea?
Yes, sir.
So these are two things. And now we will get into details of how do we find the dot product and how do we use it in application. Is it okay?
Yes, sir.
Okay. Now let's talk about coordinate system, and we'll take two vectors. So we'll look into algebra of vectors, okay?
Okay.
So let us see. We have one vector here represented like this. The other vector, let's say like this. These are my
Yeah.
two. Let's give them some coordinate points. Let's say this is 2, 1, and this point is, let's say, 7, 4. And let's say this point, let's call this as 1, 1, let's say 1, 5. And this
Yeah.
point, let's say 5, and let's say this is 9. Okay. So let me name this vector as u and this vector as v. So you can write vector u as what? What is vector u?
So we
Vector
can write it
u
as
is
5 and 3, right?
5 and 3. So I will write in a column 5 and this is 3, right?
Right.
And vector v is
4 and 4.
4 and 4. So these are my two vectors, right? So when I say dot product, what we really mean, and I'll show you the operation. We write like a dot, literally. That is
Yeah.
the dot product between the two vectors. And how do we do it? We write these two vectors, which is 5 and 3, and 4 and 4 in this case, with a dot in between. So
Right.
dot product results into 5 multiplied by 4 is what?
20.
20. And plus 3 times 4 is 12, right?
12. Yeah.
3 times 4 is 12, and we get a number which is 32, 32. Right?
32.
32, and that becomes the result of this dot product. So our answer
Okay.
is 32, which is a number, a scalar quantity. Do you see that?
Right.
So this is how we get as our result. Now, when we define dot product, how do we really calculate this? Let's look into this. If I have to do dot product between u and v, it is actually equal to magnitude of u times magnitude of v times cos of angle between them, cos theta.
Right.
So that is the definition of our dot product.
Oh, okay.
uv cos theta, right? Well, in the given example, theta was not given to us, right?
Right.
Well, we figured it out using algebra part, right? So that's the beauty of this vectors. We'll soon see how they are related, but that is how we could do it. Now, so let me now show you how we really did it. So this vector u, you could have written as what? Vector u, you could have written as 5i plus
3j.
3j. So where I is the component unit vector along x and j is the unit vector along y. And I could have written as 4i plus 4j, right?
4j. Yeah.
Okay. So let us use this particular method and then find out the same answer, right? Remember 5, 3 and 4, 4. Let me clear the screen and rewrite this vector u as 5, 3 and vector v as 4, 4, right?
Right.
Unit vectors, you write a cap on top, correct? Now, let us try to, and also I gave you the definition, and which is the dot product is defined as multiply the magnitudes of the vectors, right?
Right.
Magnitude is a scalar quantity.
Right.
And cos of theta is also a scalar quantity. So you get a scalar quantity, right? So what do you get is scalar. Do you see that?
Yeah.
Okay, great. Now, what is the magnitude of u?
So it would be square root of 5 squared plus 3 squared.
Correct. Which is 25 plus 9?
34.
Correct. So we'll write 34 for now, right? We are not going to simplify this. Is 4 square plus 4 square, right? Which is 16, 16, 32, right?
Root 32.
We write 32. I know we could write 4 square root 2, right? Okay.
Yeah.
We could write. Anyway, so 4 square. So these are the magnitudes, right? Now, how do I get this cosine theta into this? And I gave you the result. Okay. How do I relate with that result? This is what we're trying to think, right? So we have 5 I plus 3j. Okay. And we do this dot product with 4i plus 4j, right?
Yeah.
Okay. So if you apply the distributive property, what do you get? You get here 5 times 4, 20, right?
Right.
And I mean, dot product, right? I times I, right? Which is I square, right?
I squared.
And what is the angle between I and I? Cos of 0 degrees, right? Do you understand?
Oh, is it because it's the same vectors?
Same vector, right? So unit vector I, this is unit vector I, right? And that is unit vector j.
Correct.
Okay, now, let us do 5i times 4j. What do you get? 5 times 4 is 20, right?
20.
I times j, right? I times j, magnitude of I times magnitude of j, and cos of 90 degrees, right?
90 degrees. Yeah.
Now, what is cos of 90 degrees? 0, right?
Right.
So this will be 0, correct?
Right.
Now we'll say 3 times this, right? Let's do this. So we did 3 times magnitude of 3 times magnitude of 4 times I times j, right? Magnitude times cos of 90 degrees.
90, sir. So this is also
I and j are at an angle of 90 degrees, correct?
Yeah.
And the last component is 3j, 4j, right? So 3j, 4j, right? So j times j, right? J square, right? Which is cos theta 0, right?
Right.
So you can see j times j means magnitude is 1, 1. And cos theta is 1, right?
1. Yeah.
So what we get here is 20 plus 12, 32. Does it make sense?
Yes, sir. Makes sense.
Correct. So because, very simple, I dot I is magnitude of 1 times magnitude of 1 times cos of angle between them, which is 0 degrees.
Yeah.
Right. Which is also 1. So this gives you 1, right?
Right.
And I times j will give you magnitude of 1, and cos of 90 degrees.
90 degrees.
Which is 0.
0.
So you see, when you multiply, I should not say multiply, when the dot product of I and j component is concerned, then the effect is 0. You get the
right.
It is like pushing a ball.
Yeah.
There is no work done. It doesn't move.
Right. Right.
You get the idea. It doesn't move. For example, if I have to move, let's say this is the road, right? Okay.
Yes, sir.
And let us say that we have an object right there. And if I have to
Right.
move this object and I'm going to apply a force in this direction, what is the work done? What is the movement? Displacement is zero. I
0.
cannot move it in this direction, can I?
No, sir.
You get the idea, right?
Yeah.
If
So
I
0 work
want to
done.
move in this direction, applying force at 90 degrees to that results into zero output. You understand
Right.
the concept? I and
Yes, sir.
J, when you have dot product, that is how this dot product is defined.
Yeah.
So the only component which is helping it to move is the component which is in this direction.
Right. Cos of 0.
Yeah, otherwise it is zero, right? So
Right.
what we do here is that let me just again sketch the same situation. So this is our road, and we want to move this particular object, and we apply some force, and this force being like this. So if this force is being applied, then the only component which helps it in moving is the horizontal component.
Horizontal component. Right.
I component. Do you understand? F of I,
Yes, sir.
right? And the F of J will be contributing nothing in this movement
Right.
along the horizontal. Is it okay?
Yes, sir.
Which is, you can see, displacement times force work done.
Right.
Correct? So
Correct.
that is the concept. So it is very important when we read about dot product, why we are reading about it, how we can apply it, and what is the significance, right?
Right.
Is it all absolutely clear to you?
Yes, sir. It's actually clear.
Very important. So we learned that if there are two vectors A and B, right? These are my two vectors.
Yeah.
Then the dot product is magnitude of A times the magnitude of B. These are scalar quantities.
Right.
Times cosine of angle between them, cos of theta.
Right.
If you are given these vectors in the form of x1, y1, ij components, for example, right?
Yeah.
And B is x2, y2. In that case, x1, x2, right?
Right.
Plus y1, y2 is the dot product because
Dot
the
product.
other components will give you zero, right?
Right. Right.
Because they are at 90 degrees, I and
90
J.
degrees.
So that is simple way of finding the dot product. Is that clear to you?
Yes,
This
sir.
is all in R2, right? If
Right.
you have in R3, same thing, right? So only thing is x1, y1, z1 times x2, y2, z2, right? Will give you the product of x1, x2, y1, y2, and z1, z2. That is how you are going to find the dot product between two vectors. It is always a scalar quantity, correct?
Correct.
Let's have an example. So
Yeah.
we have a vector u, let's say, and we have a vector v this time, horizontal. And let me say that the angle between them is let's say 60 degrees.
Yeah.
And magnitude of u is, let us say, 4, and magnitude of v is, let's say, 3. So what is u dot v?
So it would be 6.
4 times 3, cos of 60 degrees is very fast, which is half, right? 12
Yeah.
times half, which is 6. Very good job. It is 6, just the number 6, nothing else. Number 6.
Right.
Is it clear to you?
Yes, sir.
That is how you could find it. Now, here's your test question. Be very careful while you're answering this question, okay?
Yeah.
So, I am using this vector A, whose magnitude is 5. And I have another vector B, whose magnitude is, let us say, 4. Okay, easy numbers. And the angle here is, let's say, 100 degrees. Can you now use calculator? Tell me, what is A dot B equals to? No,
Yes, sir.
magnitude of B is 4. I want to write this. Tell me, what is
So,
A dot?
The angle between A and B is 100 degrees?
No, the diagram is shown. I'm not saying anything. I'm saying that as given in the diagram.
Yeah. Okay. So it would be 5 times 4 times cos of 80 degrees, right?
Yeah, because the angle between them, you have to put them tail to tail to find the angle. So the angle between them is 80 degrees, not 100. So it will be cos of 80 degrees. You get the idea?
Yes,
so you
sir.
have to be very careful while answering that, it is to find the angle between two vectors, you have to place them tail to tail, correct?
Tail to tail. Right.
That is how we should be answering this particular question. Perfect?
Yes, sir.
Absolutely clear to you?
Yes, sir. Yeah.
Okay. So we've done a good question here. Now, I will also, so we have already seen application of dot product into a very important example, finding the work done. When a force, some Newton is applied and displacement is given to us, we can always use those two vectors and find the dot product and the answer. Okay. Now, we'll move on to the next topic, which is another very, very important application. And let me first give you the definition and you will figure out what I'm trying to say, right? So, A, vector A. Okay, vector A. Let's see, vector A dot vector B. I'm saying is magnitude of A times magnitude of B times cos of theta. Good.
Yeah.
Now let's look into a situation and see another physical real life application here. Okay, I'm making a coordinate axis. It helps us to relate things better. So what I will do is, let us say my vector B is this.
Okay.
This is my vector B. And let us say I have a vector A, which is this.
Yeah.
Fine. So this is the angle theta. Okay. Now, let us say we want to find the chapter here is projection.
Yeah.
Of A on B. You see the projection of A
Projection.
on B. So the projection of A on B will be, if I project A on B, this is the projection of A on B.
Oh, okay.
You understand? Think as if there
Yes,
is
sir.
a light here and the shadow will fall down on B. This
Right.
is what we call projection of A on B, right? So,
Yes, sir.
so this was vector. Let's say this is O. I'm just now writing some points so that it's easy for us to communicate. O to A, and this is O to B, right? And this projection comes at this point. Let's call this point as N, right? So projection of A on B is shown in this diagram as ON, okay?
Yeah.
Okay. I showed it with an arrow. It is in the direction of B. Now, can you tell me what is the magnitude of ON?
Yes, sir. So we would have to find the magnitudes of A and B first, right?
Oh, in terms of A and B, tell me.
Okay, so we can use the cosine ratio, right? Using theta to find magnitude of that.
Right, sir. So cos theta is basically equal to ON over magnitude A. Is that okay?
Yeah.
ON over A. And therefore, we can say that the magnitude of ON, which I'm showing as a vector, is basic magnitude is scalar, you know that, is magnitude of A times cos of theta.
Cos of theta. Yeah.
Okay. ON magnitude is A cos theta.
Right.
Now, so this is basically, you figured this as A magnitude A of cos theta.
Right.
Correct. So what we see here is kind of a position where we have this particular magnitude, which is a projection of the vector on this particular thing, right?
Right.
So A cos theta is basically, if I use this particular formula, dot product, then A cos theta I'm saying is ON, right?
ON, right.
Magnitude of ON times vector B.
Right.
Scalar multiple, right? Magnitude of B. You get the idea?
Yes, sir.
So you can also say that the dot product is the product of magnitude of scalar projection. This becomes a scalar projection because we are not giving it any direction. Is it okay?
Right.
So we'll call this as scalar projection.
So ON is the scalar projection, right?
Yes.
Yeah.
If I use the word vector projection, then I'll give you the direction of B, right? Because it is in B.
Right.
Is it okay?
Yeah.
So the scalar projection of A is ON, which is A cos theta. You get the idea?
Yes, got it.
You can also write the dot product A dot B in terms of scalar projection of the vector A on B times B. You get the idea? So I will rearrange the formula and I can say that ON is actually equals to dot product of A and B divided by magnitude of B.
Oh, okay.
So I have a formula for you that the scalar projection of a vector A on B can be found by dot product of A and B divided by the magnitude of B. You get the idea?
B. Yes, sir.
Very important formula. You can make a note. This is your next chapter.
Yeah.
Application of dot product.
And so this is the general formula, right?
Oh, yes, it is a general. So you can have scalar projection of any vector on any other vector, and you can easily calculate using this particular formula. And we know how to derive it, correct?
Yes, sir.
Well, I'll clear this just to remind you what we did just now. Is we learned that the dot product is a scalar quantity which could be written as product of their magnitudes times cosine of theta between them. We also learn that this dot product could be written as, because we combine these two terms, A cos theta. Yeah. And we wrote this as scalar projection, right? So of A on B. We technically write like this. We write like this. Projection of A on B. Projection of A on B times the magnitude of B. You see that? B. Yeah. Now, we will isolate this projection of A on B, and we can write this as the dot product of A and B divided by the magnitude of B. So this is the formula for scalar projection. Projection of A on B. Clear? Yes, sir. Now tell me, what could be the formula for vector projection of A on B?
Yes, sir. So for scalar projection of A on B, we did AB cos theta, right?
Yeah.
So I think the vector projection would be similar, right?
Same, but we need to give a direction.
We need a direction, right?
Okay, let's give the direction. Not difficult. You have understood the concept, right? Actually, I'm telling you, this is not an easy concept. Hundreds of students fail to understand this concept. And as soon as you have the scalar and vector projection in the test, most students will not be able to do it correctly. Guaranteed. Yeah. And see how easy it is. I have to give a direction to my scalar projection, right? And can you tell me what is the direction? It is along B, right? Because we saw that. We saw that if this is B, then the projection of A
is along B.
Yes, along B, right? So if I have to give this direction, it is a unit vector in the direction of B, right? Right. So what do I have to put it here?
So you would put B over the magnitude of unit B, right?
Perfect. Unit vector along vector B, which is the vector B itself divided by its magnitude.
Yeah.
Do you get this?
Yes, sir.
Okay. So let's write down the final formula, which is there in every book.
Yeah.
Vector projection is equal to dot product of A and B over, what is this?
The
Magnitude
direction.
of B
The
times
magnitude.
magnitude of B is what? B square, right?
B squared, right.
Times, this is vector
Vector
B,
B.
right?
Yeah.
So, scalar multiple, do you understand?
Yes,
It is
sir.
the scalar multiple of vector B. This thing is scalar quantity. Dot product divided by the magnitude square of B. You get the idea?
Yes, sir.
So we have completed another chapter apart from just dot product. Perfect?
Yeah.
So could you digest all this? Is this all absolutely clear to you?
Yes, sir. You made it very simplified, so I got it.
You got it, right?
Yeah.
So, great work. So Akshay, can you summarize what did we learn today?
Yes, sir. So today we went over the dot product, and initially it seemed pretty complicated, right? Because so many vectors and like a lot to do. But I think with the formulas that we derived and just seeing the whole process, it's much more clear on how to approach a problem now. And sir, I like the way how you related it to physics, like work done and everything. Because in my physics class, we didn't really touch upon why the box wouldn't move if it was being pressed against the ground. But now it makes sense because cos 90 is 0, right? So yeah, it's very clear now.
Even at the end of your vector class, most teachers don't talk about it, right? Until and unless they hit upon the question, find the work done, and then they go back to it. But the story starts from work done. You have to actually model the situation. How do you model the situation mathematically? Vectors is the only way to model it. And that is one reason why the vectors became so important. You get the idea. So you are learning modeling physics now. Started when you started with vectors, you said, well, sir, it is reminding me of physics, right? Scalar.
Right. Yeah.
It is actually modeling the whole book of physics.
Right.
So that is the beauty of it. Now, I like to, I'll share with you my video and then some questions. Okay. So let me just search my YouTube channel for vectors, then I'll share, right?
Yes, sir.
I'll share with you my YouTube channel and we'll look into some videos from there.
Yes,
so I just searched Anil Kumar dot product applications playlist. You will see many, hundreds of playlists with hundreds of questions. Most of the questions which you will see in my playlist are from previous test questions. They are not just ordinary questions. Okay? So we have many examples here. We'll look into one of the playlists. This has got only 15 videos, which I'm sharing with you now. So review dot product cross product concept with test questions part 1. Okay, very interesting. It is very early to share with you this particular because you haven't really learned about cross product so far, correct?
Yeah.
So, but anyway, you understand that what type of multiplications we are getting into, and you also know cross product is giving you a vector quantity. So today you haven't done that. That's fine. At least do the questions related to dot product. 43 minutes video. Just go through it, get some examples. As you can see here, question number 1, A, B, C, and D are 3 non-zero vectors such that A dot B is equals to A dot C. Which of the following is always true? Very important questions here in this particular playlist. I'd like you to pause just as we are pausing here, answer this question, and then move forward. You will get all the concepts absolutely clear as you go through this particular playlist. So many examples here. We are given that sum of two vectors is square root of A over 2. Determine the value of 3A minus B dot A plus B. So we are given sum of the two vectors and we are trying to figure out the dot product between the vectors. A and B are unit vectors. Remember that as given. Right. So very interesting questions and solutions are given to you. This exercise is on dot product and cross product exercise. Now the next video is vector dot product projection, work done, multiple choice test part 2. Very important. So you see the term projection of A on B, right?
A on B. Yeah.
So remember one thing, that the projection of A on B will not be same as projection of B on A, right?
B on A. Right.
Because in the formula, you are dividing by the magnitude
squared,
of B
right?
when you have A on B. But when it is
Right.
B on A, you will divide by magnitude of A. You get the idea, right?
Yeah.
So different story altogether. So you don't get, and then there are many questions which we'll talk about. So you have to go through these questions to understand the concept. And vector projection, scalar projection is not a simple thing. We just derive the
Yeah.
formula, right? You see that A projection on B, that is how we write, and that's the formula. A dot B, and B dot B is magnitude B square. What is magnitude
right.
B square? B dot B. Do you understand?
Right.
You do B dot B, you actually get the magnitude of B. It is a very easy way to find it, because B dot
Right.
B, x square plus y square square root, right?
Square root. Yeah.
So B dot B will be xx, which is x square, plus yy.
Right.
So dot product also gives you the magnitude square, right?
Right.
So, and you see this vector B there, and that is how you find the scalar and vector projections. So that video will give you a lot of examples, and you will understand all what we learned today. Can you please read this question?
Yes, sir. Anil jumps out of an airplane 4 kilometers above the Great Pyramid of Giza and parachutes down to its point. If the work done by gravity on Anil is 3 million Newton meters, find mass of Anil and his equipment.
Correct. So interesting question, but simple. Work done is a dot product, and using that dot product, you can find the solution. Correct. So very interesting test question before you. So that is how you should be working. And then I also introduce you to that dot product has applications in finding area and volume, right? So if you have solids, you can find area and volume using dot product. Can you please read this question?
Yes, sir. Area of a scaling triangle with dot product. Find area of the triangle formed by the vertices A2 minus 3, B14, and C00.
Correct. So if you use normal formula, you remember, if you get the coordinate points, you use Heron's formula to find the dot product.
Exactly. Yeah.
Not an easy thing. It's a very difficult task, right?
Very long. Yeah.
Semi S value, right? Semi perimeter, and then it's a long formula, right? But here, imagine with dot product, we are finding area of the triangle. Given the, you see that. Another very interesting video to look into. This is extremely complicated, high-level question, which is asked in very high-grade university examinations. Okay, so can you read this question?
Yes, sir. Vectors regular tetrahedral. Find angle between any edge and face not containing that edge of regular tetrahedron.
The tetrahedron is a very important shape. Like you have a water structure, it is tetrahedron in nature, right? So it finds a lot of applications in chemistry and in physics and real life situations. And this, again, is a question which will be solved using dot product. But side of complicated way, rated is a very high level. It comes in very university examinations, entrance examinations, where there's right? So slightly more complicated. You may look into it at the end of the session, not in the beginning. That is my suggestion to you. Now, we also saw how do we use dot product using the angles. And then this exercise is your normal test paper on dot product. Do you see that? All the questions, which is again a 52-minute video, almost an hour, you will see the questions which you have seen in past 10 years on dot product. Best from there. So that will help you to really prepare well and be on the top and stay on the top as you're already, right? Perfect. So I think this is a good playlist. I'll just give you the link. You can always search by just saying Anil Kumar .per. So with that, we can end our class. You know, there are so many things to do in the chat. I'll just put in this link. You may copy the link.
Yes, sir.
And at least do 6 or 7 videos. You'll be like, you'll know each and everything about dot product. And wherever you get cross product for now, I will like you to avoid it till I teach you about cross product and how do we calculate it, right? It'll be easy. So that'll be good. Okay. So
Okay,
is
sir.
everything absolutely clear to you?
Yes, sir. Everything's absolutely clear.
Great. Then first do my few videos, one or two, and then questions from your book. Just don't worry.
Yeah.
You will be in a position to do all the questions
Right.
related to dot product for sure. If there is any
Yes,
difficulty,
sir.
feel free to contact me. Right? Okay.
Yes, sir. For sure.
Okay. Then we'll end the class here now.
Okay.
Thank you.
Thank you so much, sir.
All
Have a
the
great day.